There's Greg Valiant from Stanford. He did his PhD from Harvard, and postdoc at Microsoft.
For Boogie?
Okay. And I know he has a bunch of nice awards. We didn't want to really mention them, so it's that. And he's done some great work in theory of algorithms. And today he's going to tell us how to make sense of Yelp review data, even if there are a bunch of lots and lots of malicious reviews. We're just trying to game the system.
Thanks for having me. The award I'm most excited about is my Google Faculty Research Award. So thanks to whoever made that happen. And so I wanted to come and talk about this stuff in part because I think it's interesting, but also because maybe you guys have some other kind of viewpoints on the sort of questions that sit here, and maybe even some data that we could try out some of these algorithms. So anyway, feel free to stop and ask lots of questions, especially since I think the slides are going to be slightly rough. So I was going to talk about a few things based on a couple of papers. So papers are joint work with different combinations of Jacob, who's probably graduating next year. He's a PhD student. Michaela's a master's student, and Moses. Sure. So one of the papers I'll mention was at NIPS last year. Another of the papers with kind of more of the heavy results is coming out at Stock this year. And then there are actually two more papers that are in submission. And I won't distinguish which results are from which papers. It'll be more of just about what problems we're talking about. So this work is motivated by the question of, so to what extent can you hope to develop algorithms for kind of estimation, for learning, for optimization, that are robust to a significant fraction of untrusted data. Okay, so this setting that we'll sort of think about is you have n data points. Alpha n of them, for some parameter alpha, are drawn from the distribution that you actually care about. And then we make no assumptions on the remaining 1 minus alpha n data points. Okay, so these remaining data points, maybe they're biased, maybe they're noisy, maybe they're arbitrary, or maybe they're kind of maliciously planted as a function of the alpha n good data points. What can you say in this regime? Yeah, and the goal is going to be to kind of answer the questions we'd like to answer kind of almost as accurately as if we actually knew which were the alpha n good data points. Okay? Which is that's kind of the gold standard, right? If you actually knew which are the data points that are drawn from the thing you care about, then you would have just run your usual learning algorithms on these, and that's that. Okay, so this is the setting where we'll be. Okay, I probably don't need to belabor the motivation, but here's the motivation. So does anyone remember this tweet? This was an Associated Press tweet from, I think, 2014. It says, breaking, 2 explosions in the White House, Barack Obama injured. So this was a Associated Press tweet from, I think, 2014. And this is what this is the Dow Jones Industrial Average. This is what happened when the tweet was made. And presumably, so what happened, right? Someone hacked the Twitter feed of the Associated Press. They probably shorted a bunch of stocks. They posted their tweet, and then they offloaded their trades. I'm not sure what the time scale is. I mean, things were fixed within 5 minutes. And to most people, they see this, then they check a few other websites, and they realize that what was happening. They realize that, well, you have lots of automated algorithms sitting on news feeds and Twitter and all this stuff, automated trading algorithms that are trying to trade rapidly based on developing stories. They see this, they all go crazy, they short a bunch of stuff. And by the time people realize what's happened, when people realize this is fake, then the damage has been done, and then things revert. Okay, so you can't actually really make money this way. I mean, the trading exchanges, they they roll back the trades that happened as a result of this to discourage this sort of thing. One reason they do that is because there's lots of machine learning things sitting on top of
How do they roll back?
How did they roll them back? So as I learned relatively recently, when you sell stocks, they like sell, and then there's 3 days later that you get the money. And in those 3 days, presumably, they're doing something, which is checking.
Making money out of it.
Probably, but among other things, they presumably want to be able to reverse things.
Okay.
I don't Janera and I bought a house last year, and we didn't realize that it takes so long to get your money out of the market. A little bit of a problem. Anyway, so right, so this is just an illustration of, for example, how even a tiny bit, a single kind of malicious data point can cause haywire. So slightly more, so seriously looking forward, there are kind of the obvious security vulnerabilities of the future, which are sort of, as we have more IoT devices, so Nest stuff, and certainly self-driving cars. That's my understanding. You guys maybe can or cannot correct me, maybe. A lot of the self-driving cars are based on data that's being beamed back by the, for example, like there are lots of Teslas on the road. Presumably, they're beaming back data to Tesla, and you could imagine if you say first I buy a Tesla, a short Tesla stock, I cover my garage with video screens and beam back some absurd data that makes it seem like every plastic bag that floats in the middle of the road is a big rock, and now maybe whatever learning algorithm Tesla's using will end up breaking every time they see a bag in the road or something. Right? So you can easily imagine if you have machine learning things sitting on top of data that you don't really know where it's coming from, this could be a big security vulnerability. They're more kind of mundane, or I shouldn't say mundane, but question of how do you enforce online community behavioral standards, right? So Twitter certainly seems like they have been wanting a good way of enforcing behavioral standards on communities. And you say, oh, well, why don't you just have like a like or a flag button? Well, people will use that. Well, how can you be robust with this sort of stuff? Crowdsourced data curation, peer grading. These are other kind of applications, right? So some of these MOOCs have experimented with peer grading, where you shuffle around the returned homeworks to students and you ask them to grade things, and then you always have a big coalition of 20% of the class that's all from the same little block of colluding entities, all trying to complete their grades. Okay, even more broadly, there's often some trade-off between the amount of data that you can collect and the quality of the data. So if you have some fixed budget for collecting data, you can either get an enormous amount of garbage data or a tiny amount of very good data. And it's worth understanding the value of cleanliness in your data. Okay, so and it's worth being able to understand this without really needing a model over what the garbage data is, right? You'd like to, you don't want to assume that the bad data is just random noise, since it's probably not. Okay, so a bit of context of this sort of stuff. So there's been a long history of work in kind of robust statistics community looking at exactly these sorts of questions. What happens when you have some data drawn from a reasonable distribution and the rest of the data maybe is arbitrary? Most of the work from the robust statistics community has kind of looked at very specific metrics of what happens when you have this sort of setting. So there's this notion of the breakdown point of estimators, which is basically how much. So you tell me some estimator of some property you care about. The breakdown point of that estimator is the fraction of bad data that you can tolerate, such that if you have more than that amount of bad data, the estimate can become arbitrarily absurd. So say I have the mean of a bunch of points. What's the breakdown point of this? All it takes is a single data point that's absurd, and you can make the mean of a set of things as funny as possible. So the breakdown point of the mean is basically 0. All you need is a tiny little bit of a single data point. Something like the median, what's the breakdown point? Like half, right? Because if you perturb more than half of the data, you can make the median absurd. If you perturb less than half of the data, no matter what you do to that half, you can't make it arbitrarily absurd. This is the notion of the breakdown point. There's been a lot of work studying what estimators have good breakdown points, what have bad breakdown points. There's also the notion of kind of influence, which is how much influence can a single data point have on estimators. So this is good work, it's old work. Ideally we would have a much more kind of accurate and nuanced and holistic understanding of what happens as the amount of information, as the amount of bad data increases. Okay, so this kind of misses a lot of the picture. Sorry. Right, so we'd like to understand, as you increase the amount of bad data, information theoretically, how accurate can we hope to be? And how do you do this in a computationally efficient manner? For the learning theorists out there, so there's this notion of agnostic learning, where you're saying that we make no assumptions about the data, and we just ask, can you find a hypothesis which is as good as possible for this data? So maybe you're learning a linear separator. You're not making assumptions that your data is linearly separable, but you're asking what's the best linear separator for this data. This is kind of this agnostic learning is a very different viewpoint. And many of the punchlines are that agnostic learning becomes NP-hard. Okay, so there's a nice result of Moritz's part and Anker Moitra that says, suppose I have data in high dimensions that it all lies in some hyperplane, except 10% of the points don't lie in that hyperplane. A bunch of points on some hyperplane, 10% of the points aren't on the hyperplane. How hard is it to find this hyperplane that goes through 90% of the points? It can be NP-hard. Okay. So that's sort of an example of this kind of NP-hardness that comes out of this agnostic. Okay. There's been some very recent progress in kind of the setting this kind of robust setting that we'll be talking about. So there are these two independent papers, Diakonikolas and friends, and Lyra and Rampala, and they both thought about this problem of robustly learning a Gaussian distribution in high dimensions. And in particular, they're thinking about robustly learning this distribution in the case where the fraction of good data is more than a half. Okay, so maybe 80% or 90% of the data comes from the nice Gaussian. What can be done when 10% of the data is arbitrary? So I wanted to illustrate kind of the intuition for why, in many cases, you should be able to do well when the majority of data is good. And then we'll go on from there. So say our goal is to learn, so say I promise, this is a very contrived example, but say I promise that the good distribution is some sphere, say of radius 1, and your job is to learn the center of the sphere.
Uniform over a sphere, or?
Yeah. I mean, this is
Not a spherical Gaussian.
no. Although the results will be the same. But, yeah, so uniform over a spherical disk. Your job is to learn the middle, and a third of the data could be arbitrary. The other 2/3 are continuous. So what can happen? So in one dimension, say this is this little strip is our one-dimensional, uniform distribution. So what can the adversary do? Well, in some sense, the worst thing the adversary can do is kind of put all its mass here. Now I have no idea, is the truth a spherical disk here, 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 here? I have no idea. Okay, in 2 dimensions, well, what if the adversary, so this is the truth, this is where the garbage data points lie. So this looks absurd, right? If this was the case, you'd say, well, this is obviously garbage, this is what we want, we know the answer. So what's kind of the worst thing that the adversary can do? Well, the worst thing is kind of something like this, right? To make this kind of moon-shaped thing. But now we don't know where the center is. The truth could be anywhere. And in 3 dimensions.
Is that obvious in the specimen?
No, it's not obvious. So this is basically the intuition for both the results, the previous results of Diaconopoulos and Round and Paula. And this is kind of so the intuition is, in this sense, if the adversarial data points are kind of too weird, then you can identify them and remove them. And the intuition is that things should improve kind of the higher dimension you go, provided that a distribution you care about is kind of nice. Okay. So this is my summary of the. So both of those 2 previous papers, they're big papers. They do lots of stuff. This is the intuition behind those results. Okay. So we'll come back to why you'd care about this other setting, but consider a setting where the majority of the data is actually untrusted. So say only 1/3 of the data comes from the thing we care about. So in some sense, there's this kind of obvious impossibility, right? So say this is a good thing, and the kind of arbitrary or adversarial data forms these other 2 spheres. There's obviously nothing we can hope to do, right? We can't tell which is which, and there's no way we can always figure out the good stuff, right? Yeah. So this is kind of this obvious impossibility with dealing with the majority of untrusted data, which is one reason why the statisticians kind of didn't go down this path. Okay, but let's try to handle this case anyway. Yeah. So so there are 2 notions. So one is this kind of list covering learning notion, which the kind of variant of it was proposed by Balkin, Blum, and Paula in 2008 to kind of a clustering setting. Think of it this way. So again, we have n data points, alpha fraction are drawn from the thing we care about, no assumptions on the remaining ones. And now suppose the goal is to return a list of maybe 1/alpha answers. So in this case, instead of just trying to return 1 answer, maybe the goal is to return 3 answers, such that at least one of them is correct. And there it's kind of trivial in this case, right? You do 1, 2, 3, those are our 3 answers, at least one of them is correct. Okay, so at least conceptually, if the only hurdle to learning in the case where you have a minority of good data is that you can't decide among a few different options, this isn't a big deal. Right? I mean, a different way of phrasing this is it the case that the arbitrary data can really hide the structure in the good stuff? Or can it simply, try to confuse you by adding other copies of things that kind of look like good stuff? And that's what this question is kind of getting at. Okay, so the second setting which we're proposing, which is maybe more relevant to the kind of practical settings. So again, we have the same setup. But additionally, we're allowed to take k, and think of k as a tiny amount, maybe a constant amount, of verified data points that are drawn from the distribution of interest. Think of this as we have our huge, dirty data set. It's a mixture, maybe a minority of it is good data. And then we have our, highly paid workers who collect a very small data set that you really believe. And now you're asking, how can you use your k, your small amount of trusted data points to extract information from the big one? And at least in, in this silly example, it's trivial, right? All of the good data points will be from the blue thing, and then you're done. So again, here the kind of conceptual question is, how can the kind of availability of a tiny amount of trusted data help you extract information from a larger but untrusted? Okay, so I wanted to give a different motivation for the setting where a minority of the data is trusted. Okay. So this I kind of describe as a data prism or database prism. And think of the following slight caricature. So suppose you have a very large data set of customer product evaluations. You have M products. Think of M as thousands, maybe. Each customer evaluates some small number of products. So maybe each customer evaluates 5 products. So you have this huge data set sitting somewhere. And then suppose you come back to this data and you want to understand, what does the student demographic actually like? What's, say, the vector of average preferences for students? So again, this is like we have our large data set, and we want to pull out the student demographic. So you can think about this as, you can map this into the previous framework by you just say, okay, students correspond to the good data. Everyone else corresponds to the arbitrary data. Can we actually extract the properties of the student demographic? And in this semi-verified model, this corresponds to saying, well, additionally, what you're going to do, you're going to take your big data set, you're going to hire a very small number of students, pay them each to evaluate some very small number of items, and use that little verified data set to pull out the student demographic from the statement. Okay. So here, I wanted to give a flavor of the results for this, right? So, so the results imply that you can hire a constant number of students. Each one will review a constant number of items. This is our verified data. And then we can use this together with a large data set mixed between demographics to pull out an accurate estimate of the student demographic preferences on all of the items. Provided the fraction of students in the original data set isn't tiny. And we actually get so if everyone evaluates 5 products, we're okay as long as the fraction of students is at least 1/2 to the 5, which is pretty.
You don't know who the students are on the original data set.
Yes, yeah. So that's the point.
And the constants depend presumably on the fidelity of the estimate, right?
Yeah. So right. So the amount of noise and the good stuff comes into this, but it's you still have this kind of nice exponential thing on your side. So again, the motivation for this was kind of some of maybe some of the medical settings where like you have tons of medical records, and suppose you figure out that 5% of the population has a certain mutation, and now maybe you can find a set of 100 people who have this mutation and look at their medical histories, but there's no hope of getting of figuring out which of these people in your billion-person medical data set has this mutation. So the question is, how do you use a small amount of verified data to pull out information about some small cohort or some small fraction of the big data set without actually having those labels? Okay, so so if you had the student labels, it would become okay. Are we okay with the motivation setup?
And this notion of student is a stand-in for being able to sample uniformly at random from whatever the underlying demographic that you're trying to pull out. That's
yes. So right. So okay. So when we formally state this, so in this case, when we formally state the theorem, we'll be assuming that there is some vector preferences for students, and each student is going to independently, with some noise, like have an unbiased estimate of this vector. So I mean that is a
So if the students are bimodal or something, that's already you don't get the same kind of results. So I'm hearing you're assuming spherical Gaussian for
or in a binary setting or in a numerical setting, as long as each thing is unbiased in each coordinate, then but that implies kind of even modality. We'll come back to this. But that's a good question. Okay. Okay. So going back to the the general settings. So say you have M items, N reviewers. Each reviewer evaluates R items. Think of R as small, 5, 10. Some constant fraction, some alpha fraction give you noisy but unbiased ratings. And we make no assumptions about the remaining reviewers. And then after the fact, we can get, say, a constant number, K, of, say, random reviews for the demographic of interest. And these, again, might be noisy, but are unbiased. So the question is basically, how many items does each person in the big data set need to review? How many verified trusted reviews do we need in order to be able to get pretty accurate estimates of all of the items? Okay, so one observation, which is not, seems intuitive. So I claim if R equals 1, so if everyone in the big data set evaluates a single item, then there's nothing you can do. You really do need to obtain verified data for everything. So why is this the case? Well, yeah, okay. Does this intuitively make sense?
So what is the form of the data? We just know which item each reviewer chose to.
Say we randomly assign people to review items.
Oh, okay, and it's the.
And you get their value for the item. Maybe it's binary, but maybe it's a 1 to 5 scale, or. And in some sense, by definition, the good people are giving you unbiased estimates, because the mean by definition is the average rating for that item among that demographic, and the bad people can be doing arbitrary things. So yeah, so I claim if everyone just evaluates one item, then there's really nothing you can do, and you need to evaluate all of these items yourself using the trusted data. And the question is, if everyone evaluates 2 items, can you do better? 3 items. Okay, so we have two theorems. So, so the first theorem says it's okay to, with each person reviewing 1 item, you can't do anything. If each person reviews some constant number of items, independent of the number of items, dependent only on the fraction of good people and the kind of error estimate that you care about, then it's okay to have just a constant number of verified data points. So you can do this. So with each person reviewing 1 item, you can't do anything. With each person reviewing some constant number of data points, you can do it with just a small constant size trusted data set. And it's okay to have the number of people reviewing things be on the same order as the number of items to review. Okay. Sorry, so this n is the size of your data set, right? So this is extremely sparse.
You perhaps meant omega of m?
Sorry?
You meant omega of m, right? Because if you have more people reviewing items, that's perfectly fine, right? More people.
Yeah, sorry. So it's okay even if you just have a suitably large constant here.
Data, in that case.
Yes. Well, yeah, but the constant needs to be sufficiently big. But, yeah. And then the second theorem is that if you really care about having each person in the big data set evaluate very few items, then it's okay to have the number of items each person in the big data set reviews be actually logarithmic in this fraction of good people. As long as you have lots and lots of data points in the original data set. So if you have kind of n squared people reviewing n products, it's okay if everyone just reviews 2 products. And you'll be able to couple. So these are kind of 2 different bookends. So one is the regime where the total number of items is comparable to the total size of your big data set. And the other regime is kind of where you have many more people evaluating things than the size of your big data set. And in both cases, it's okay if everyone evaluates a constant number of things, and you only need a constant number of verified data.
Wait, is it m to the r? Isn't m the number of?
Sorry, this is m to the r. Yes. Okay, so should I So maybe I'll start by describing kind of the first theorem, and then maybe we'll okay. So think about yeah. So imagine the matrix of customer reviews. Okay, so think of this as like the Yelp thing. So each person has rated a few items on a scale from 1 to 5. Each column represents an item. Each row represents the evaluations of some person rating. So each row represents the customer. Each column represents an item. And this is a matrix of ratings. So sorry, ignore this for now. Okay, so if we assume that the good reviewers are independently, in a noisy fashion, but independently giving unbiased estimates of each product, then what happens? Well, if you were to look at the submatrix of this, consisting of the good reviewers, again, we don't know where they are, but imagine someone told you which the good reviewers are. I claim that this submatrix would be, it'd be very sparse, it'd be very noisy, but it would basically be low rank. Why? Because in some sense, each of these rows is a very sparse, very noisy, but representation of the same underlying set of preferences. Okay. And so each of the good rows are noisy, sparse, but copies of the same underlying row. Hence, this is basically a noisy, sparse rank 1. And then the question is, to what extent can the arbitrary extra rows that are interspersed destroy this noisy, sparse, but basically rank 1 component? Okay, so you got this nice part of the matrix that kind of is coherent. You have this other stuff that's trying to hide this part. To what extent can you hide this part? And the answer is, to some extent you can't, right? So there is this nice sort of rank 1-ish component. What can the rest of the matrix do? Well, it can make other nice rank 1 components. It can say, oh, look, here's another nice rank 1 component. Here's another nice rank 1 component. This corresponds to kind of the, like maybe there are different sets of preferences corresponding to these different rank 1 components. And then at the end of the day, you'll use your verified data to figure out which is the one you care about. Okay? It might be slightly surprising that this is all an adversary can do. And you need to be a little careful about how to actually pull this back out. So so how do you actually do this? Okay, so you'll solve this convex program. I'll kind of describe what this is. So you're going to basically say, come up with estimates of the underlying probabilities for this matrix. So actually fill in this matrix with all of them with ratings. So as to do the following. The way you fill in the matrix, it should be as similar to the actual matrix of ratings as possible. So you want to kind of fill these things in without changing much, but subject to some bound on the nuclear norm of the matrix that you come up with. So you can, so intuitively, what might you want to do? You might want to say, find me a low-rank approximation to this matrix. Okay, that's a little too sensitive to what these other garbage rows will do. So instead, we're basically going to say, yeah, come up with some matrix that's similar to this, but has smallish nuclear norm. And also, you need to make sure that no row of this new matrix you come up with is kind of too powerful.
So why do you need the nuclear norm?
Yeah, why do you need the nuclear norm? So if you had, okay, so what are the other options? So the other options are you could do a kind of Frobenius norm.
Trace.
Right. So
between 1 with infinity.
yeah, right. So or I mean between 0, 1, and 2.
0 is not enough.
Right. So yeah. So I think you'd like to do 0, right? And this is kind of not an option. It's not computationally it's not convex, it's not nice. And kind of doing the nuclear norm is kind of doing as close as you could hope while still being computationally feasible. So it's a nuclear norm. I mean, this is just the sum of the singular values.
Can use, for instance, an even tighter bound of x1, 2 more.
Yeah.
Then
I think that
then
might-
you will get that almost like construction that every row is not powerful.
Right. Although you do want to trade off kind of the discrepancy with the original thing and how much power it has here. I think using this, 1 to 2, I think it works. This maybe it's slightly
Question is, what's
simpler.
the proof?
Yeah.
Okay.
A few other things here where Frobenius doesn't work.
So the good reviewers are a low rank submatrix because you say assuming that they all have similar valuations for the different items.
Yeah.
And what is the noise model?
Sorry?
What is the noise model?
So as long as the noise is bounded and each of the good people stay unbiased and independent over items, which is a big assumption.
And how much noise, like
As long as it's bounded, say here it's bounded between 1 and 5 on each thing, then it's okay. As long as it's unbiased. And again, so it's not actually low rank, right? So if you have a random, say I have a single row of probabilities and I have a matrix where each row I pick a constant number of entries and then flip coins with those probabilities and have this random sparse matrix. This won't actually be, that low rank. It will be, or you can't reconstruct the original probability using naive low rank approximation. Although once you can prune out heavy things and so on, then you can get it back. Right, so this is like random graphs with constant degree. Spectrally has some issues, but you can fix it. But getting between like logarithmic sparsity and constant sparsity, you can do. It's a little hard. That's swept into this. So yeah, if you aren't more careful, I think you might need logarithmic to the 1 to 2. But anyway, I kind of just wanted to talk about this at a high level. But at the highest level, yeah, we're going to come up with a surrogate for each row, which is similar to the rows, but subject to kind of having lowish rank and making sure that that we're not susceptible to any one data point pulling us too far away. And that's all it really takes. And intuitively, this makes sense.
So other reviewers are not allowed to collude?
No, they are.
They are collude, right?
And they are allowed to collude. And the point is, how would they collude? The only thing they can do is they can form their own lower rank subspace over there. But that's fine. We'll take our constant number of verified things and figure out which of these lower rank subspaces we're actually in.
Okay.
And if they try to collude to kind of hide this lower rank thing, that's what we're showing kind of can't happen. So
the intuition is that if you were to actually get by, which is low rank, then one of the components would be the correct,
yes,
corresponding to the
exactly.
correct fraction.
Yeah, so you have a biggish lowest rank robust component. At worst, you could have a few of these, a constant number of them, 1 over alpha, and then you can figure that out.
Sorry for giving you more time.
No, please.
So it seems like the bound on the nuclear norm is at least 1 over epsilon squared, because R itself is only 1 over epsilon. So it's you have is there a little lower bound for that?
Well, but no. So this is, I mean, this is on the matrix Y that we're coming up with, right? Which isn't going to have any sparsity.
Okay.
Right. So we're coming up with a dense matrix. We're saying, yes, you rated 5 items. We're guessing everything that you would have rated. We're trying to do this in a consistent way, right? So the nuclear norm on Y could be enough. So we're trading off this, its norm with subject having a smallish norm. We're trying to have it as similar to the rating.
Right. But if epsilon is small, you have dependency of at least 1 over epsilon squared. That's what I'm saying. Because R by itself is also fall in one over epsilon.
Oh, you're just saying what this is.
Like whether the bound is
Yeah. So
vacuous. I don't want to say that. It's very
oh, I see. Whether this is yeah, no, I mean it's not.
what's the power for R in terms of epsilon?
I think it's going to be, so we started off and it was like 1 over epsilon to the 4th, and then maybe we get it to be to the 3rd, getting it down to squared seems hard. So it's not, yeah.
Well, that's why I said it's 1 over epsilon squared after it's squared.
Right. So the punchline is after you do this, you end up with a matrix of kind of the guesses of everyone's ratings. And the guarantee will be that all of the rows corresponding to the good people are actually close to the underlying truth. And then you can use the verified raters, or in this list recovery model, you could just kind of sample a few things and then you're done. How many people here know about the robust PCA stuff that Candes and Co did? Yeah, so that's a slightly different setting. There you have a low rank matrix with sparse noise, and you're trying to recover the low rank matrix. This is a little different. In some sense, you have a low rank matrix, but it's not sparse noise. It's instead you have a smallish, or maybe lots of rows which are completely arbitrary. So in some sense, this is kind of strictly more general than that. And the techniques look similar, but a little more.
So if you had a confidence rating on each reviewer, instead of being able to solicit K extra reviews, I would interpret that, because I think most likely these systems do have some reviewers who they know are.
Yeah. No, so that's a good question, right? So certainly, I mean, right. So I think you would end up, maybe you'd rate agreement more for those ones, but then you'd also allow those rows to be a little more powerful. I'm not sure how this would filter down,
but can you use that to filter out the bad rows?
So again, it's this distinction that we're not necessarily trying to remove the bad rows, because maybe the bad rows aren't bad. Maybe they're kind of just like, maybe the student demographic is just like everyone else, right? So at the end of the day, maybe you don't know who's good and who's bad, but you get the answer corresponding to the good. Okay. So imagine taking the same framework, but trying to do much more ambitious learning and optimization with it. So I'll say something if it makes sense, great. If it doesn't, never mind. So instead of kind of thinking of getting ratings from n people, imagine we observe n convex functions, of which some alpha fraction are drawn from some distribution over convex function. P star, say that's the ideal distribution of a convex function. We make no assumptions about the remaining 1 minus alpha convex functions. And the goal is to find some W that minimizes the expectation of a function drawn from the thing we care about of f of W. So say we've sampled a bunch of convex functions, we're trying to find a point that kind of minimizes the expected function. And I claim that this is actually and again, maybe we also have some verified functions that we know have been drawn from this. So I claim that this is actually a strict generalization of a lot of the problems that we've, of the problem that we thought about. Okay, so you can think about f sub I is kind of the loss function corresponding to some data point that you've sampled. So in the case of ratings, the previous example, yes, we're given these data points, x1 through xn, but you can interpret one of the data points as corresponding to this loss function, so the ith data point f sub I of some value w is the square distance between w and x sub I. What point minimizes, so if I have a bunch of these things, what point minimizes this loss function over the data set? The average xi, right? So this loss function, just so we have a bunch of random points, and we want to find their mean. That's the same as viewing each random point as a sample of this loss function, the distance squared to that point. Okay, it's a convex function. And now the problem of minimizing finding w that minimizes the expected loss function is the same as finding the average point, which is the same as like aggregating these ratings. Okay? The same as finding the mean rating vector. Okay, but we could put different convex functions in here. So instead of trying to find the mean, we could also ask about doing linear regression or other kinds of optimization. Yes, no, maybe.
But here you kind of lost the ability to put a generative model, right? In the previous setting, you were able to succeed. You were able to get around the lower bounds by assuming that the rows that are good are actually coming from a fixed distribution.
So we're still assuming that, and the question is, what are the properties that we need about this distribution, P star distribution over these convex functions that let us do this? Okay. And sorry. So informally, the thing we need is that kind of the matrix of gradients of the functions drawn from our class kind of have nice concentration, meaning that they're not kind of. It's not like one of these functions says no, go over here, and the other says no, go over here. That they're all. Okay, let me actually strip this. So the way to prove results for this is basically the natural intuitive extension of the way to do it in this other setting. And that now we have our n functions, and we're basically going to guess good points, w's, for each of these functions. So we want one w, which is kind of good for all the good points. Instead, with each point will get its own w, and we're going to kind of trade off the objective function value for each of these things. So we want w1 to be good for the first function f1. We want w2 to be good for the second function. But subject to these w's, most of them kind of agreeing with each other. Okay, so how do you capture this? Most of them agree with each other. Well, we're going to kind of require that these w's, they all sort of are contained in like a smallish ellipsoid, with a smallish trace. Okay. But just think about this as so we have all of these different convex functions. We want to find one solution that's good for most of them. Sorry, that's not good for most of them, but that's good for the good ones, the ones coming from the good data. And instead, we kind of have a answer for each of them, subject to them not being, the answers not being completely all over the place. Let's see about that. Okay, so I should wrap up, right?
Do you mind going back?
Yes.
Yes, I'm missing some data. Okay, let's take it offline. It's going to become technical.
Okay. Okay. So at a high level, this. So what's the punchline? So even in this kind of more general optimization, regression settings, we can get some strong positive results saying, yeah, you can do regression of these things, even if you have a very small fraction of, or a small constant fraction of good data. How good are the guarantees? They're not great. So we have this very general result for any specific setting you care about. Say you only care about regression, there's probably a much sharper sort of result you could get, especially if you're willing to make stronger assumptions about the distribution of data points. So think of this as more saying you should be able to do computation efficiently, you should be able to do something good for whatever kind of learning setting you care about. The actual result you get is probably more of a theoretical sort of interesting thing rather than something that you actually would run. Okay, maybe I'm not going to describe the stronger result of how to get fewer ratings and deal with a tiny fraction, this inverse exponential amount of good data that you, amount of, if the fraction of students is really, really small, I won't tell you how to do that. It's a more combinatorial algorithm. Okay, instead I'll just end with the kind of story. So, so in general, especially like this kind of where theoretical computer science meets kind of machine learning, there are a few different paths you can take. So one of them is kind of worst case analysis, which usually ends up being kind of too pessimistic in that either you can't do anything or everything is kind of NP hard. And this is kind of the agnostic learning setting. In many cases, you just, computationally things get very hard. A different option is you can kind of start pursuing maybe average case or distributional assumptions. Say, okay, well, if noise is random and this is distributed like this, then you can kind of get your wildest dreams in terms of results. And then in some cases you apply those to practice and you get complete garbage. And in many cases, these things are very, very brittle to the, to the assumptions you make. And this sort of stuff on this kind of robust, semi-verified, learning, one hope is that it gives strong positive results, computationally and information theoretically. And it seems to require relatively weak assumptions. And that, yes, you're making assumptions on the good stuff. You're not making any assumptions on the bad portion of the data. And, it remains to be seen whether these things will translate well into practice. But I'm pretty optimistic, in part because the sorts of algorithms you get out of this seem like they're kind of very robust things that kind of smell right. Okay, maybe I'll end here.
Isn't the small one supposed to be just right?
I thought it was the medium one that's just right.
No, it's the kid's ball.
No. I'll fix it.
So are you planning to evaluate any of this in real data?
Yeah, so we had some we have some real data, but so it's all the real data we have. It has all been startups are like, oh hey, it'd be great if we could do this, and then at some point they're like, no, actually, like you can't say anything about this data. So it's hard to find people willing to share.
Don't scrape it off of like a Yelp or.
Yeah, so that's the other thing. That it would be good to have a setting where you actually have the true underlying. That you understand the underlying truth, and this is also
So you can take real sort of academic data, publicly relevant data, and corrupt it. Right?
Yeah. So again, so I know. So Jacob's played around with this a little bit. So yeah. So ways you think about corrupting things, this does tackle, and it does a good job. Whether it tackles the kind of stranger, malicious behavior of your Yelp at the restaurant across the street keeps giving you bad ratings. It's hard.
You talk to Zervas?
Sorry?
You talk to Zervas? Yurios? Yurios at
no.
Reach out to him. He's been looking into what breaks Yelp for a long time, and I think he's been scraping things shamelessly.
Okay. I've talked to Michael Bernstein, who does kind of a lot of crowdsourcing stuff. And some of the stuff he does is, how do you aggregate? You have a bunch of crowdsourcers who are trying to label your data set, and half of them just kind of click together, and half of them have 5 other aliases put together. But anyway, yeah. So I'm not sure what the real killer application this is for. Whether it's for trying to get algorithms that you really want provable guarantees for. Like if you have a self-driving car, you really want to be sure that it's not going to do a crazy thing if you get arbitrary data in. So I'm not sure if the real applications are, security type things versus data cleaning. But it'd be
Because a self-driving car is also kind of tricky because some outliers are actually very important and you want to take care of them, right?
exactly. But I mean, if any of you guys have like big product review data sets or something, it'd be cool to try to run some of this on that.
Send us interns.
Okay. Yeah, let me know if you guys have interesting.
Thanks.